Hello everyone. Welcome you all to second week problem solving session of the course Introduction to Group Theory, which is NOC 26 MA 12. I'm Priyanka Sharma, your PMRF NPTEL TA, and I'm from Indian Institute of Technology, Patna. So let's start. So first we recall the topics covered in second week's course lectures. So the course is Introduction to Group Theory. So what is a group? Group is a non-empty set, say G, with a binary operation star, and the star is defined from G cross G to G. And by the definition, this binary operation star is closed. And if we assume three properties and those three properties are satisfied by this binary operation star, then we say that this G is a group and those properties are associativity, existence of identity, and existence of inverse of every element in G. Again, this group G is said to be abelian or commutative if A star B is B star A for all A and B belongs to G. So we saw that for a fixed group G within binary operation say star, the identity element denoted by E is unique. That is, there is one and exactly one element E such that A star E is A, and that is same as E star A for all A belongs to G. Again, we say for a group G star, inverse of each element is unique in G. That is, for all A belongs to G, there uniquely exists some B belongs to G, which is usually denoted by A inverse, such that A star A inverse and A inverse star A are same as the identity element. Okay, and one more thing. And suppose we have some elements, say A, B, C, and D belongs to G, and we want to find their operation under a specific order. Say A star, B star, C star, D, which can be usually denoted by A, B, C, D, if the meaning of the binary operation star is clear. Then if we preserve the order, like A, then B, then C, and then D, if we preserve this order, then we can pair the bracket as we want, or we can say that we can extend the associativity property. Like particularly we have for three elements, say A, B, and C belongs to G. If we want to find this word A, B, C or A star, B star, C, then this can be written in two ways, A star, B star, C, as well as A star, B star, C. That is, we just, we just, change the way how we bracket the elements. that is this one. And here this is okay. So the order is same, that is A, B, and then C. So this is the associativity for three elements. How we can generalize this? So consider a question like, let G be a group for some fixed elements A, B, C, D, and E. Here this E is any element of G. This is not particularly the identity element. So for A, B, C, D, and E belongs to G. Consider the element, or say the binary operation of these five elements in a particular order, say A star, B star, C star, D star, E, or simply A, B, C, D, E, then find out the ways find out how many groupings we can do to find this element. Okay. It means we want to find the number of ways in which we can place the brackets, place the parentheses, basically. So how to do it? For three elements, we have these two ways, but how to generalize it for, say, four elements, five, six, and so on. So we take a particular example with five elements. Okay. So how to do it? So suppose we have, say, n is the number of fixed elements of G, and we want to like we want to group, or we want to place parentheses for these n elements to find the product. So if n is 1, that is, we just have one element, say simply A. So this is basically a trivial case. We have binary operation start, that is, we need two elements to perform it. So for simplicity, or like to preserve the generality, we just say that there is a single way. Now come to non-trivial cases. For n equals to 2, that is, we have two elements, A and B belongs to G. So we can do simply in one way. Hello. Please mute yourself.
Okay, I am muted.
Okay, thank you. Okay, so for n equals to 2, again we have one way. If n equals to 3, that is, if we have three elements in G, then we have already seen that we have three ways, A, B, and then C. And first we perform the binary operation between B and C, and then with A. So this is basically like if we see this in a general way, we have three elements, A, B, and C. Then what we can do, we can pair these two elements and then we consider this. So here we have two elements. So we have seen that if we have two elements, then there is just one way to pair them. So from here we have one, and for just one element, again we have one way. So here basically we have 1 into 1, that is one way. And if we pair these two, then again from here we have one way and from here we have one way. So again we have one, and total we have two ways. So if n equals to 4, that is we have four elements A, B, C, and D belongs to G, then what we can do, just write A, B, C, and D. If we leave the first element, then we have three elements here. So this one element, this can be paired in just one way. This is a trivial one. And for three elements, what we can do, we have two ways. So here we have two ways. Now, if we pair first two elements and then last two elements, then here we have 1 and 1 corresponding to this case. So here we have 1 into 1, that is one way. And if we consider first three elements, then we have two ways from here and one way from here. So we have 2 into 1, that is two ways. So total we have five ways. Similarly, if we have five elements, then what we can do? One and four, like how we can break it? So from here we have one, here we have five ways, that is five. If we break this five elements in two and three, so okay, for two elements we have one way. For three elements we have two ways, so two from here, like one into two. If we break it in three elements and two elements, then we have two ways from here and one way from here. So we have again two ways. And if we break it in four elements once and then the last one, so again we have five ways. So total we have 14 ways. So similarly we can generalize this. So what was the question? We had five elements. So how many total ways can be there? 14. Now next question. Which of the following statements are true? First, if every element of G, where G is a group, is inverse of its own, that is, it is self-invertible, then G is abelian. Second, the converse statement of this, that is, if G is an abelian group, then A inverse will be A for each A belongs to G. And the third statement is uh, for a group, say G, and consider two elements A and B belongs to G, such that order of A is pi and this B is other than identity, and there is a relation between A and B, that is if B square is AB A inverse, then G is abelian. Okay, so in this question we have these three statements and we need to find which is true. So there can be more than one true statements. So let's consider them one by one. So the first statement, let G be a group. It is given that for each A belongs to G, we have A inverse is A. Okay, that is inverse of every element is the element itself. Okay, so what we can say, G is abelian or non-abelian. So G will be abelian if AB is BA for any two elements, A and B belongs to G. So what we can do here, we can consider two elements, say A and B belongs to G, then AB, this will again be in G. Why? Because G is a group. So the binary operation between A and B, that will be closed. That will again give an element of G. So now this AB is an element, and what we have, inverse of every element is the element itself. So what will be the inverse of AB? It will be the element AB again. So now from the given assumption, AB inverse is AB, but we have AB inverse is B inverse A inverse, which we have already done in the previous problem solving session. So we have B inverse A inverse is AB. But again, for the elements A and B, what will be the inverse of those? So again, B inverse will be B and A inverse will be A. So we have BA is AB. And as A and B were any arbitrary elements, so we can say that G is abelian. Now, what about converse? Is the converse true? That is, we take an abelian group, then can we say that the inverse of every element will be the element again? So let G be a group with the property that A inverse is uh, so, G be a group such that AB is BA for all A and B belongs to G, that is G is abelian. So we can think about examples of abelian groups. So we have this example Z plus. This is an abelian group. So is this property A inverse is A true for this group Z plus? What will be the inverse of elements in Z plus? What is Z actually? Is set of all integers. and we are considering additive inverse. So inverse of 0, that is 0 again. So yeah, that is this condition is true for the element 0. But what about 1? What will be the inverse of 1? Inverse of 1 will be an element such that 1 plus the element will give us the identity. And what is the identity? That is the additive identity. That is 0 here. So inverse of 1 is minus 1. But 1 and minus 1, obviously they are distinct. So A inverse is not equals to A for all A belongs to G. But G is an abelian group, so we can't conclude that in an abelian group, A inverse will be A for every element A. Okay, so the first statement is true, but it's converse, that is the second statement is not. Now, what about the third one? We have a group with two elements, and we can see order of A is 5, that is the element A is other than the identity element. And again, B is a non-identity element. And we have this condition, that is B square is AB A inverse. Then can we say that G is abelian? So let's come to this. Since B square is AB A inverse. Okay, and we have that order of A is 5 and order of B, okay, B is not equals to identity. Actually, this order of A is 5. This also implies that A is other than identity. Okay, so is the group G is abelian? So suppose we consider, what if G is abelian? If G is abelian, then B inverse is AB A inverse. This can be written as, like, we can break it like this, and this will be A inverse B. Like, we can use the commutativity here. And again, by associativity, we have A inverse B, and this will be the identity. So this will be B, that is, we have B square is B. So we can apply the cancellation law and we will get B is identity. But we have assumed that B is other than an identity element. So this assumption cannot be true. That is, G is non-abelian. So the statement is a false statement. Next, let G be a group if G has exactly one element of order 2, then that element commutes with every element of G. Okay, so what is the question? Like, for a group, if the group has exactly one element with order 2, then the element will commute with every element of order G, like every other element of G. So what is this order? Order of an element. So in the previous session, we have seen what is order. I just want to recall this. Suppose we have a group G and some element A belongs to G, then there exists, okay, okay, then some non-negative integer n is said to be order of A if A n is the identity element, and this must be smallest such element. Okay, so if we have a smallest natural number n such that a n is identity, what is a n basically? This is a star a n times. So in multiplicative group, this can be a n and in an additive group, this can be na. Okay, so if like a star a up to n times, if this is the identity element of the group, then we say such smallest natural number as the order of the element A. And this is denoted by order of A is n. Now come to the question. For a group G, there uniquely exists an element A such that order of A is 2, then the element will commute with every other element. Okay, so there is a result. Let G be a group, then order of A is order of G inverse A G. For all G belongs to G and some fixed A belongs to G. Okay, so the proof was discussed in the previous session, which you can refer by the YouTube video. Okay, so what we can do with this, uh, order of A is 2 as well as order of G inverse AG. This is again 2 as order of these two elements A and G inverse AG are same, and this is true for all G belongs to the group G. But what we have said that A is the unique element in the group G with this property, that is with order 2. That's why this A and G inverse AG can't be different. Now G is a group, so multiply by G from left, what we will get? G inverse AG. Now this will give you GA. This is the identity AG, and this will be GA AG. So this is true for all G belongs to G for a given A. So it means that the element A commutes with every element of the group G. Okay. And the next classes we will discuss a term which is center. So like from here, we can say that this unique element of order 2 is a member or an element of the center of a group. Okay, so we will discuss it in next classes. So next question. If P is an odd prime, then there is no group with exactly P elements of order P. Okay, so how to do it? What we are claiming here, let G be a group and we consider this P, which is an odd prime. Okay. Then we say that there is no group with exactly P elements of order P. Okay, so how to do it? So we have the element P itself, or let's do it in general, not restrict with the group. So let A belongs to G such that order of A is P. That is, we first we start with an element uh, which has the order P. Here P is a node prime. Okay, so what we can do again? We can consider the subgroup generated by A. So what is a subgroup? Recall this. So subgroup generated by an element. So let G be a group and A is an element in G. Then the subgroup generated by A, which is denoted by this, like A within angular brackets. So this is the collection of all A to the power K. Let's consider K belongs to set. Okay, so come to here again. Consider this. Consider the subgroup of G generated by A. That is this. So what we can say about this subgroup? The subgroup generated by A has exactly p minus 1 elements of order p and one element of order 1. Mm, that is the identity one. Okay, so what will be A? So if we consider its like non-negative powers, so that will be A naught, A1, A2, and so on. But we have this order of A is P. That is, A to the power P is identity. And identity is basically A to the power 0. It can be written in this way. That is, this element, this is identity, and this is the element A itself with order P. So we have A to the power P is identity. It means we can go up to A to the power P minus 1 only. And then A to the power P will be this element identity. And again, we can write A to the power P plus 1 as A to the power P A. So A to the power P will be identity. So A to the power P plus 1 will be A, and A square will be A to the power P plus 2, and so on. So it means we can have at most these P elements in the subgroup generated by A. Now, till now we have seen that we can have at most P elements, but uh, how to say these are exactly P distinct elements, like there is no repetition. So we claim that all the elements are distinct. All the P elements in the subgroup generated by A are distinct. Suppose if possible, any two are same, say AI is AJ, where I and J, these are greater than or equal to 0 and less than or equal to P minus 1, and I is not equals to J. Then what we can conclude? We can conclude from here like AI, A to the power uh, minus J, like we are taking inverse here because A is an element in a subgroup generated by A. So A inverse will be there. So this will be this, and from here we have A to the power I minus J. This is identity. So without loss of generality, we can say like I and J, they are not same. So suppose we consider I is greater than J. So this I minus J is greater than 0, but this is less than P obviously because I and J both are less than or equals to P minus 1. So this contradicts the fact that order of A is P. That is A to the power P is identity and P is such smallest integer. Okay, so this cannot be true. That is, this cannot be true. This can be like possible if and only if I and J both are same. Otherwise, this cannot hold. So that's how we can say that the subgroup generated by A has exactly P elements. Okay. And what about the power again? This has exactly p elements. And identity has order 1. So what about the remaining elements? They have same order, and that is the prime number p. So actually order of this subgroup, this is p, so it cannot have any element whose order is other than the divisors of p, and p is a prime, so it has only two divisors, 1 and p itself. That is, every element can have orders either 1 or p, but there cannot be more than one elements of order 1 because identity is unique. So that's why remaining p minus 1 elements has order p. Okay. Therefore, the subgroup generated by A has p minus 1 elements of order p. Okay. But what we were trying to construct? A group with exactly p elements of order p. So till now we get p minus 1 elements of order p. It means we need another element, like one more element which has order p. Okay. So suppose b is some element which is not included in subgroup generated by A. It means like it assures that this B is uh, distinct from these P minus 1 elements of order P. Okay. Such that order of B is P. But again, we can consider this subgroup generated by B, and it will give us P minus 1 elements of order P. So we started from this. Here we get P minus 1 elements of order P. If we want to include an element B with order P, then again by closure property, we will have to consider the subgroup generated by it. So this will give us again P minus 1 elements of order P. So from here, we will have twice of P minus 1 elements of order P, which is greater than P. So it means we cannot construct a group with exactly p elements of order p. Is it clear? Therefore, there is no group which has exactly p elements of order p. Consider an a statement and then say whether this is true or false. A group of even order must have an element of order 2. Okay, so is the statement true or false? Hmm. So let G be a group such that order of G is even. That is, order of G is some 2n, or we can simply say order of G is greater than 1. Okay. So the group G is non-trivial. That is, we can have a non-identity element in G. So there exists some A which is other than identity belongs to G. We can have this. Okay. So case 1, if order of this A is 2, then we are done. Okay. Second case, if order of A is not equals to 2. Okay. It means we cannot have any element in G with order 2. Okay. Like we have already excluded the identity uh, with order 1. And if there is no element, there is no element of order 2 if possible, then what we can do? We have some sub cases. Uh, if order of A is not 2, but if this is a multiple of 2, then so if order of A is say some 2m for m greater than 1, otherwise it will be 2 itself. Okay. So if this, then we can consider this element A to the power m. This will give us an element of order 2. Why? Because this one, order of A is 2m. This implies A to the power 2m is identity. That is A to the power m. A to the power m, like if we compute it with itself, we will have the identity. That is, we can say that order of A to the power m is 2. So in this way, we get an element of order 2. Okay. So come to next subcase. If there is no element of even order. Okay. That is, every non-identity element has odd order. Okay. Now, if order of A is greater than 2, then A and A inverse, they are distinct. Otherwise, if A is A inverse, then we can have A inverse is A inverse. Okay, fine. Say A. This is A inverse A, and this is how we get A square as identity. That is order of A is 2. Okay, which is a contradiction. So that's why if order of A is greater than 2, then A and A square, they will be distinct. Okay. But order of A is order of A inverse. Okay. This is what we have discussed. So in this way, we can pair these elements A and A inverse. Okay. So we have some elements in the group G. We have already excluded the identity element, and we are considering only non-identity elements, and all has odd orders as per our assumption. Okay. So from those non-identity elements of odd orders, A and A square, they will have same orders. Okay. And they can't be same. So we can have this pair A and A inverse. This is not an ordered pair, like just consider them simultaneously. Okay. Similarly, if B is an element of odd order, then B inverse will have same order. We can like compute them simultaneously and so on. So this is what all non-identity elements of odd orders, we can pair them. Okay. It means uh, like from this pair we will get two elements, from here we will get two elements and so on. So how many elements we will get from here? We will get even elements from here. Okay. We have even number of non-identity elements of odd orders. Okay. We cannot have odd number of like such elements. Okay. Because we have elements in pairs. So they will contribute two. Okay. So obviously we will have even numbers from here. Now, even number of elements from here and we have one element identity. So collecting them, we will get odd number of elements only. But group were of even order. Okay. So this is a contradiction. That's why we will have a non-identity element, but order of G is even. So there must exist some non-identity element whose order is not odd, that is even. Okay. So whenever we get a non-identity element with even order, we can come to the subcase 1 and from there we can get an element of order. Okay. Okay. So the statement is true. Any doubt? Okay. Now, let G be a group. For a group G, let we have two elements, A and B. Let A and B belongs to G and A and B, they are distinct. Then either A square is not equals to B square or A cube is not equals to B cube. Okay. So how to check it? We have a group G and we have A and B belongs to G such that they are not same. Then either A square is uh, other than B square or like A cube and B cube, they are not same. So suppose if possible, A square is B square and A cube is equal to B cube. Then what will be the trouble in this case? So consider this A cube equals to B cube again. We can write it as A square A is B square B, but B square is A square. So we will get A square B from here. Okay. And now we can apply the left cancellation rule for this element A square. We will get A equals to, which is a contradiction to this. Okay. Therefore, A square and B square and A cube and B cube, they can't be same in pairs simultaneously. Okay. Therefore, either A square is not equal to B square or A cube is not equal to B cube. Okay. Consider another question.
Uh,
Uh,
excuse me, like
mhm,
A and B, A and B belongs to the group. Okay.
mhm.
So if I'm taking like suppose mod 3, suppose mod 3 with if I'm taking the group with the mod 3, 0, 1 and 2 are the elements.
Okay.
So like 1 is not equal to 2.
Mhm.
So 1 square is 1 and 2 square is 4 and 4
Wait,
mod
wait,
3 is
wait,
1.
wait, wait. Uh, actually, mm, what is the binary operation in that case? Like, say I'm denoting it by Z3 if you are okay with it, or Z over 3Z, whatever that is. What is the operation?
If I'm taking multiplication 1, suppose.
Multiplication, suppose if possible. So actually
Mm,
Z3 is 0, 1 and 2. 0 cannot have an inverse.
that will not form group. Okay, under
Yes, so
multiplication.
we'll have to consider plus. And
Okay.
actually A square means A star A.
Okay.
Okay, fine. So say
If
A
I'm
is 1, B is 2. Okay, then A square will be 1 and 1, 2. A cube will be, that will be 0. And B square will be 2 and 2, 4, that is 1. And B cube will be,
A square will be 1, no, ma'am?
uh,
Not 2.
A square will
1.
be,
1.
okay. Uh, so actually I'm considering A square as A star A. Here
If I'll
actually
take if I'll
2A.
remove 0 from that z mod 3, if I'll remove 0, then I've got two elements, 1 and 2. So 1 and 2, so they
Okay.
are the distinct elements. So I think it is satisfying the property over here.
Mm-hmm. Yeah, this is group. Mm-hmm. So A is 1, B is 2, A square will be 1. Mm, actually, this is similar as 0, 1, isomorphic 1. Okay. If you write it simply like this, what will be B square?
1 b square will be 1, 4 divided by 3, like 4 mod 3 will be 1.
Okay.
But cube 1 it is not, I think, waiting cube, because a cube is 1 and
Mm-hmm.
b cube
What
comes out
is
to be
B
2.
cube?
2
Hmm.
again, 2 it is coming 2.
So
So
actually, what I was saying, like either they are distinct or they like uh, both the pairs a square b square and a cube b cube can't be same simultaneously. At least one pair consists of distinct elements. So here this will serve.
Got it. I think what we have proved means if a square equal to b square, then a cube will be means if I'm considering one of both the cases I'm considering, then it will not form. Means I'm getting a little bit that what we are doing here. Got it.
Yeah, right. Okay. So next question. Let G is a set containing all the elements of this form. 2 by 2, sorry, this is A again. And A belongs to R and A is non-zero. Okay, that is G is a set of 2 by 2 matrices over real numbers, and this like all the four elements are same and they are non-zero. Okay, then check that G is a group. And what will be the element? Under multiplication. Multiplication means the matrix multiplication. Okay. And okay, so I will include the next condition after proving this. So how to do it? G is this A, and A, where let's write it combinedly. And our claim is this G dot is a group. This dot represents the matrix multiplication. Okay, it means we need to check four conditions. First, whether this multiplication is closed or not. So consider two elements A, B, okay, sorry, A, and another one with all four elements same belongs to G. Obviously, we have A and B, both are other than 0. Okay, so what will be their multiplication? We are taking usual multiplication of matrices. This will be AB and AB, that is 2AB, 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 2AB. Okay, so first thing, all four elements are same. And secondly, A and B both are non-zero. And 2 is obviously a non-zero, and we have the real numbers R. So we can say that this 2AB is non-zero. Therefore, this element is again in G. That is, the multiplication is closed. Second one is associativity. So associativity holds for all matrices. So that's why this is something obvious. See, we didn't change the binary operation. Okay, it has the usual sense. That's why we can say that associativity follows from there. Okay, if we change the operation, we need to check whether the operation is associative or not. Okay. Third, identity. So what will be the identity element for this set? So let this E, and E belongs to G with non-zero E belongs to R, such that this element with any element A belongs to G. This is arbitrary one. As we are willing to find the form of this element which we are claiming that this will be the identity element. Okay. So we need here
Is it come
again,
consider half?
yes. So we need this. Okay. For all these elements belongs to G. So from here we will have 2AE equals to A. It means E will be half. So the identity will be uh, this element. Okay, so half is non-zero and this is a real number, and like we have already found this element considering this assumption. Okay, and yeah, similarly we can have this also, like A, and identity this will be again this element. Okay, so this is the identity. Now what about the inverse?
In the same way, we can take like B and B. Let B be the, yeah, or A dash will be the
Okay, say it A
uh,
dash, no problem. So let this is G. Uh, Consider some A dash, which we are saying like this will be inverse of this.
and which will be equal to half. Like E to already we
Hmm,
have calculated, so now by
yes.
multiplication we can find the half.
See, we have already assured that mm, like all these elements are same, as we are taking A dash, A dash, A dash, and A dash. And don't forget to check whether this A dash, when we will get its value, is a non-zero number. Okay. So such that when we operate these two elements, we will get the identity. And identity is all half. That is 2A dash is half, which means actually we need to find the value of A dash in terms of A. So that will be 1 by 4A. Okay. So what will be the inverse? Inverse of all A this will be 1 by 4A. Here A is non-zero. That's why this element is well defined. So this is the reason why we excluded 0. Okay. Otherwise, we will not be able to define the inverse. Okay. And this is 1 by 4A. So again, this will be a non-zero number. So this will be Okay. So in this way, we will have inverse of every element. Therefore, G is a group. Okay. Now, here's a thing which is to be noted that they explain why each element of G has an inverse even though the matrices have determinant as 0. Okay. So what we study in linear algebra actually, that uh, if a matrix has 0 as the determinant, then that matrix will not be invertible. That will be a singular matrix. Okay. But here, all the matrices are all the of the form A, 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 A. So what will be the determinant? That will be 0, but still all the matrices are invertible. So how? Like, what is the case here? Like, why we are getting this contradictory thing?
Ma'am, what I think, like the when we are considering the general matrices, so
Mm-hmm.
there when we talk about the identity elements, so identity matrix, that is one
Mm-hmm.
0 and 0 1.
Right.
If it is 2 cross 2, so here the identity element is not as 1 0 0 1. So here we have got half of half all. So that's why I think determinant concept will be not applied here. I think so.
Exactly. Actually, in both cases, identity is different. But like this will be the identity uh, in GLR2 or GL2R, like what is the way of writing? And identity of G, this is something different. So yeah, this is the reason. Good. Come to the next question. Let H1 is a subgroup of H2, which is again a subgroup of some H3. So say this is an ascending chain of subgroups of a group G, then prove that their union is again a subgroup of G. Okay, so basically here we are considering a chain of subgroups of a group G. Okay, we are not taking any arbitrary subgroups. So what we need to prove here, say this H, which is arbitrary union, is a subgroup of G. So how to do it? So in lectures, mm, we have like uh, some necessary and sufficient conditions. If you uh, watch lectures by sir, then you can have some conditions. necessary and sufficient conditions for a non-empty subset of a group to be a subgroup. Okay, so the first one is like we are taking G is a group, and H is a non-empty subset of G. Then this H will be a subgroup if we have some necessary and sufficient conditions. So the first one is AB belongs to H for all A and B belongs to H, and A inverse belongs to H for all A belongs to H. Okay, that is, this is the closer one and this is the existence of identity. So we don't need to check all the four axioms. If we uh, check whether the binary operation in G, when we restrict that to the subgroup, the subset H, if that is closed and inverse of every element of H is in H itself, okay? Obviously in G, the inverse will be, but if we put an element in H from G, then it will bring its element with it. So this is the meaning. So if we have these two conditions, then we can say that H is a subgroup and vice versa. Secondly, when we combine these two and we say that AB inverse belongs to H for all A and B belongs to H, then we can say that H is a subgroup. Uh, Note that for these two, we are taking G as an arbitrary group. Like we are not restricting the order of G. G can be finite or infinite. But
Ma- Ma'am, one
yes,
question can I ask? Like when we are
hmm,
saying this subgroup, so it must be that means here we are not considering like order of the group, but when we are
hmm,
saying a subgroup means ki the subgroup order must divide the group. No, that is necessary
right.
condition.
Hmm,
Okay, it should not means suppose the group has eight elements, so subgroup cannot have the suppose group has nine elements. Let's assume so its subgroup cannot have four elements. No,
right.
okay, this I'm asking.
Yes. So actually, like Lagrange's theorem and many other results, yeah, we will discuss that, but in later classes. Okay. Actually, like here, I'm just discussing the necessary and sufficient conditions. If we have a non-empty subset and we want to check whether this is a subgroup or not, then what we can do? Okay, so these two conditions, first and two, these are in general. Okay, this can be true for a finite group and for an infinite group both. But if we have uh, G is finite, okay, then uh, we can have these like A, B belongs to H, this is sufficient. Like if for each pair A and B belongs to H, we have A operated by B belongs to H again, then we can say that H is a subgroup and vice versa. Okay, we don't need to check whether A inverse is in H or not. Okay, that will follow from the fact that G is finite. Okay, so come to the question again. Here, actually, we are taking any arbitrary chain. Okay, this is not a finite chain. This can be or cannot be. Okay, so we cannot go with the third condition. Okay, so we need to check either first one or second one. So second condition is actually something more convenient. So we will pick this. So we need to check whether this H is a subgroup of G or not. So first, uh, is this H non-empty? So yes, since all HIs, I varies from 1 to so on, are subgroups of G, so identity will be there. Therefore, this identity will exist in the union. Actually, this identity element exists in all the subgroups. Although here we are taking only like union, so existence in at least one HI will be sufficient, but we have existence in all the HIs, so fine, we have some more than sufficient kind of thing. But still, uh, identity belongs to H, that is the union. Therefore, we can say that this is non-empty. Okay. Now, we take two arbitrary elements, say A and B belongs to H, which is union of HIs. So if A and B belongs to union, it means A and B belongs to some HIs. So say A belongs to HJ for some J belongs to N. We are taking natural numbers, 1, 2, 3, and so on. And B belongs to some H, say K, or some K belongs to N again. Now we consider maximum of these two, J and K. See, that is L. Then A belongs to HL and B belongs to HL. Why? Because we have a chain. Okay. So HL will include HI and HJ both. Okay. So now this HL is a subgroup of G. Therefore, the second condition is true. So AB inverse belongs to HL for any pair A and B belongs to HL. Okay. Now AB inverse belongs to HL for some L. It means AB inverse belongs to union. Therefore, this union is a subgroup of G. Okay. So one more thing I would like to mention here. Let G be a group if H1 and H2 are subgroups of G, then H, which is their intersection, is always a subgroup. Okay, so this is true for like arbitrarily many subgroups in general. If HI are subgroups of G, then H, which is intersection of this, is a subgroup. Here, HIs can be non-comparable, like we don't require any such chain. Okay. But what about the union case? Let G be a group if H1 and H2 are subgroups of G. Is this H, which is union of H1 and H2, a subgroup? Always? We didn't take any relation, any inclusion property between H1 and H2. They can be comparable, they can be not. So, in general case, can we say H1 union H2 will be a subgroup? See, this is basically a particular case of this statement. Here we are taking arbitrarily many HIs, but here we are taking only two for simplicity. Okay. So, see, if we have this H1 is a subgroup of H2, then by these result, we can have uh, the conclusion that H1 union H2 is a subgroup of G. But if not, if this, then by above result, H1 union H2 is a subgroup of G. Okay, if H2 is a subgroup of H1, then no problem. Actually, we just shuffle the indices. Okay, uh, this will again form an ascending chain of subgroups in G. So this will be again a subgroup of G. But what if these two cases are not there? That is, neither H1 is a subgroup of H2 nor H2 is a subgroup of H1.
It will be not a subgroup because I think closure property will not satisfy then. Maybe, may not be because it is not confirmed. The closure property will satisfy.
Right. So can we have any counter example for this?
Uh, like for the can we go with the modulo 5 in that we can create two subgroups and then we can check like like 0 1 2 3 4 if I'm going to part in the uh, two subgroups like 0 1 and 2
Mm, don't forget to uh, the
in
fact
addition
that
means
the binary operation
operation
can be a restriction.
yeah in addition I'm just any in addition I'm taking then
Mm, if you are taking this, so this will have five elements. Okay. So if we take usual addition, so this will not be closed. Okay. So you need to take like modular addition here. Modular 5.
Yes.
right? But
Yes.
if you want to consider this as this is a non-empty subset, but can this be a group? Is this closed?
No, no, no. This is not a
No,
subgroup.
because we can't change the operation. Like this plus didn't mean like any general addition. Okay. With respect to this z over 5z or z5, this is basically modulo 5 addition, right? So this can be a subgroup or this can be a group like in general, but we need to take like modulo 3 addition in this case. Okay. But one thing which we can do, we can consider the entire Z as a group, and we have subgroups in it. So it has subgroups only of the forms NZ. Where n belongs to actually Z plus and 0. Hmm. Okay, so can we do something here? Suppose we are taking this 2Z and 3Z for simplicity, like all the multiples of 2 and 3. Now this is different from this. Okay, so this is basically the set of all elements of the form 2n, where n belongs to Z plus union 0, and this is say 3m type. Okay, and consider this 2z union 3z. Okay, it means it will have elements of the form 2n and 3m. Okay, it will have two types of elements. So either like the form of element will be 2n or 3m. That's it. So simply we have 2 belongs to this and 3 belongs to this.
But
Now,
five, like if I'm going to add five, what belongs to?
yes, this will not be in this set. So this is not a subgroup. G, which is right here. Okay. So for union, we need either of these conditions. Like either H1 is a subgroup of H2 or H2 is a subgroup of H1. Subgroup or subset, they are same. Actually, like we have already considered H1 and H2 as subgroups of G. Okay. So if H1 and H2 are subsets of G such that H1 is a subset of H2, then yeah, obviously H1 will be a subgroup of H2. Same. Okay. What is the time? Okay, we have 15 minutes. Mm,
Ma'am, excuse me, like you have
mhm.
explained alternating group, or still we have to cover that alternating group you have not taught me so far because I've joined late, ma'am, just now. Means
Okay.
1 hour late. Alternating group you have not explained no, before.
No, not much actually. Okay, so like which kind of properties you want to discuss?
Actually, I don't have the idea for the alternating group, like which type of group we called it as alternating group. Like permutation group, though I'm understanding little that composition of the permutation group also I'm understanding, but alternating group like A4, A6, something like that is I didn't have that much concept of that. So
Actually, alternating groups are not yet discussed by professor, so that's why I didn't include in problem sessions. See, I'm waiting for 1 or 2 more weeks. Then I will include like in the either in the problem solving session or actually I'm planning to make a short video, not of 2 hours actually, mm, 20 minutes or something like that. Other than this sessions, and I'm planning to upload in that channel. So will it work?
Yeah, ma'am. Yeah, like actually, here the when we have studied now in the first year graduation, first year the group actually, that much concepts are not very much clear. Like just we have got the
I
notes and
understand.
just we have seen the notice. And but what you are explaining each and every concepts now, it's very much clear, ma'am. I'm finding it like we are able to understand each and every points that how it is happening and what is the concept behind it. And here
Okay.
some and so one more like they have the like Galva group or Abel group. This
Mm-hmm.
also actually
Mm-hmm.
have uh, that little bit confusing. Like which type of groups we called it as Galva group. That also
Hmm.
actually I don't have the
I
that because actually, now when we go with the further higher studies, like so
Mhm.
group theory is totally involved in that because the very much
I agree.
first foundation is the group theory only. Then only we are
Mhm.
able to understand that what is going on. Otherwise, it's not possible to understand a
Right.
single line also.
So, we can do two things actually. Like, see, construction kind of thing and like the general definition or representation, that we can discuss like right now, or like I can upload the video today itself. But if we want to include some more things like subgroups or cyclicity or like order of elements or some kind of like isomorphism or like that kind of topics, then we need to wait for some time. So uh, what I can do, I can make separate videos for some special kind of groups or some special classes of groups.
One
So
more like
one
ma'am.
separate video can be for alternating groups.
Yeah, ma'am.
But other than
Just
definition and construction, we need to discuss some more
if
properties
no,
or.
no
Mhm,
actually Galva group is related to the construction part. No, this I'm
mhm,
not getting. I don't have that much idea. Like Galva group is mainly of the construction, I think. Huh? And
hmm,
one uh, one more, I have the confusion. Like when we talk about like homomorphism is the property of the function. Okay,
mhm.
and like when we say that it is isomorphic or something, so actually what we are correlating this also I'm not very much comfortable that actually why we talk
Okay.
about the isomorphic, because I think something for the structure part or with the properties I think they correlate with the another one set. So that also I don't have the clear picture that in which problem should we look for the isomorphic cases. That also
Okay.
I think
So.
when
Mhm.
we'll progress slowly, we'll be able to understand, ma'am.
Sure, but I think introductory videos can I make like mm, either like today or in this week only. Like what is definition, how to construct those classes, and what will be the representation and all. further advanced properties, we can make like part 2, part 3 kind of things. But yeah, introduction, I'll try to make videos.
Okay,
Okay.
thank you, ma'am.
Okay. Uh, Here I want to mention a few more things. Subgroups of Z plus. So the first thing, this 0, this will be a trivial subgroup. Secondly, every subgroup of Z plus will have the form NZ. Okay. Where this N can be Z plus union 0. Okay. Negatives can be managed by the fact that NZ, if this is a subgroup, then it will include the inverse also. So there are some more things. We can say some more properties like NZ union MZ is not a subgroup in general. Okay. Uh, we have seen an example for 2Z and 3Z. Their union is not a subgroup. NZ intersection MZ, this is a subgroup. Okay. But what will be the form? Like, as we say, every subgroup can be written as NZ. Okay. So here we need some K and then Z. Okay. We need some single non-negative integer here. So what will be the value of that K?
LCM of M and N.
LCM.
It depends.
Okay.
Like, because the common elements will be the, I think, LCM only. It will come.
Mhm. Uh, like for example, consider this 2Z and 3Z only. They are subgroups of Z. So 2Z intersection 3Z. Okay. So what will be the form of elements here? Uh, if some say say some A, such that this A belongs to 2Z and this A belongs to 3Z as well. That is the set of all those A such that A can be written as 2M and 3N for some M and N belongs to Z. Okay, means A equals to 2M means if I write same notation, don't get confused. This is M divides A and this is N divides A. Okay, that is uh, wait.
Sorry, ma'am.
Mm,
I think two
I
divides
think
A and
here 2 and 3 we need to. mm,
yes.
yes. What does it mean? Like if 2 divides A and 3 divides A, then
Then six divides A. That means uh, six Z.
yes. Okay, which is LCM of 2 and 3. Hmm. So this is like that is A is something like A is some 6K for K belongs to Z. Okay, so this is how we can do it. Now, what about some NZ and MZ? NZ plus MZ. What about this? This will be a group. I mean, this will be a subgroup.
No, ma'am, I think not, because we have a counter example of 2 plus 3 does not belongs to 2z uh, plus 3z.
Mm, see, what is the form of this?
Um,
What is the difference between these two? Uh, NZ union MZ and NZ plus MZ. Plus means we have mm,
like
eh,
it contains
I
three
think
elements.
I'm using different kind of notations. I hope you are comfortable with that. I mean, like here, I took n equals to 2 and m equals to 3, but here for like multiples, I took m and n again. So I hope that is not a problem for you all. Okay.
Yes, ma'am.
Uh, okay. So what's the meaning of nz plus mz? It means say nx plus my, where uh, n and m they are fixed and x and y they belongs to z. Okay, this is the meaning.
Yes,
Yes, ma'am.
ma'am.
Okay, so what is the difference actually? NZ union MZ, it means you are just collecting the elements. If you have some x here and some y here, then in union you will have x as well as y, and obviously some more elements. Okay, but if you are taking nz plus mz, then what you are doing? If x is here and if y is here, then you are taking all possible um, plus, like you are operating x and y. Here, in case of union, you are collecting, but here in case of plus, you are operating, because here the plus is the binary operation itself. Okay, the binary operation under which z is forming a group. So here this plus is that binary operation. Okay, so
Mm.
here x and y they will be in nz plus mz, but x plus y, that will again be in nz plus mz. Why? Because you are taking the operation between them also. So this is the difference. Like in case of this example, 2z and 3z. So if you take union, you will have 2 and 3 only. But if you take plus, you will have 2, 3 and their summation, that is 2 plus 3, that is like 5. You will have that also. Okay. So this is the difference. So,
Okay, ma'am, I got.
okay. So you can refer the lectures. I think lectures of week 2. I'm not recalling the like exact number of the lecture, but yeah, you can find that from mm, the page. And a proof of this, like why NZ plus MZ is a subgroup, that is discussed by sir. Okay, so yeah, that is a subgroup. And actually, you can do it like if you take uh, any x and y belongs to NZ plus MZ, then how you can write that, and then you can check closer and inverse. You can do it, no problem. Just keep this thing in mind that you need to include the operations also. Okay, so NZ plus MZ is collections of all NX plus MY. Mm, this is a subgroup, but as we are saying that every subgroup is like some this NX kind NZ. So this NZ plus MZ, this can be written as some KZ, where Z is some fixed integer, or K can be computed using N and M. Okay. So what will be the value of K here? Hmm. Any idea?
I think it will be 1.
Mm, 1 in this case, 2Z and 3Z?
2Z and 3Z, or if like we have to see 2Z and 3Z, it will be 1 because we'll get all the, by combination, we'll get all the integral values, we'll get Z itself.
Yes.
So I've taken the example with 2 and 3. So if M is not a multiple of N, like this also we have to see, like then definitely K value, I think it will be GCD, one day it will come. GCD of M and N, if
Yeah.
it is.
Okay. Vaibhav, you were also saying something?
No, ma'am, I was just thinking about like I was thinking that
If you have
2x.
any guess or any idea, any clue, you can share.
Ma'am, can I ask a question here? It's a different question.
Yes.
Um, does the LCM of n comma n belongs to the group NZ plus MZ?
LCM.
Yeah, LCM of
Like LCM of
n comma m belong to the group NZ plus MZ or not? That's the question.
yeah, yes, that will. Mm, see, LCM will be in the group. Okay, let's have another example. Take this 2Z and 4Z. Or, okay, we can take this also, but for now, 2Z and 3Z. So what will be LCM of 2 and 4? That is 4.
Yes, ma'am.
Okay. And 4 belongs to this NZ plus MZ.
Yes, ma'am.
See, okay, come to this again.
I mean, 2x plus 4y can take any value like 4 or anything.
Right, right. See, actually, the thing is NZ plus MZ, this this is collections of NX plus MY. And yeah, here X and Y can take any values from Z. So this is actually the form of D, which is GCD of N and M. There is a result, Bijut's identity. Like if N and M belongs to Z, and GCD of N and M, this is D, then there exists some integers x and y such that nx plus my, this is D. Okay, so here,
Yeah, yeah. I think this is the
this,
without theorem.
yes,
Yeah,
exactly. So nx plus my, this is D, which is GCD. So see, if GCD is there, then why not LCM?
yeah. Um, I mean, we can generate the whole group with the D only.
Yes, we can generate the whole group with D only. So LCM will be a part, or that can form a subgroup of the entire like NX plus MZ. Okay. So yeah, the elements generated by LCM, that will be in this NX plus MZ. Okay, but that will not cover the like whole group. Okay.
Yes, ma'am. Yes, ma'am. I understand.
Okay. Thank you. So yeah, this is NZ plus MZ. This is KZ, where K is, mm, I'm erasing this, otherwise this will make confusion for you. Where K is GCD of N and M. Okay. Just one thing I would like to mention here. If you take all N and M as 0, you cannot compute GCD. Okay. So you can't take N and M both 0 simultaneously. So like this cannot be a case. Actually, this is a trivial thing, but you cannot do this. And similarly, LCM cannot be uh, computed, or that cannot be defined if you take any like LCM of N and M. If anyone is 0, you cannot define. So for non-zero elements, you need to define this. For 0, this will be
Uh,
trivial. So, yes.
Ma'am, you're saying like if elements, any one of the, if I have to find LCM and SCF of any two numbers. So if
Mhm,
any one of the number is non zero, suppose out of two,
mhm.
any one is zero, so we can't find LCM also, we can't find SCF also, no?
We can find
Like
GCD.
like if
HCF we
one
can
number is
find.
three, one number is
Mhm,
three, another number is zero.
mhm.
So what will be the SCF of this, means GCD of this 3 comma 0?
Fine. By definition, uh, what is GCD?
GCD is the highest common divisor.
Yes.
And it should be positive always.
Should be. Yes, it should be positive. LCD of say A and B. So say if this is D, then D divides A and D divides B. And if there exists some C such that C divides A and C divides B, then this C will divides D also. Okay, like D is the greatest integer such that it divides A and B. So the question is, okay, we are already running out of time. Fine. GCD of 0 and 3. It means um, we need a positive number which can divide 0 also and which can divide 3 also. So what about 3? 3 divides 3, no problem. But can 3 divide 0? Okay, when we say A divides B if there exists some M such that B can be written as MA, like M belongs to Z, obviously. Okay, this is the meaning of divisibility. So can we say 3 divides 0?
Yes, ma'am.
So 0 can be written as uh, 0, 3. Like, yeah, there exists 0 belongs to Z such that this holds. Okay, so
So,
you can handle divisibility with this. So to define GDC, we need at least one, like if we are taking GCD of only 2 elements, then at least one of them should be non-zero. You cannot define GCD of 0 and 0. Okay, but for LCM, both A and B must be non-zero. Okay. Okay, so
Okay.
should we discuss
Okay.
some more questions or?
Three.
Mhm.
3 and 0 LCM will be not defined means.
Yes,
Okay. So if I have
this
to take the
cannot be
three
defined.
numbers, if I have to take three or more numbers and one number is zero, so LCM is will write that we are not going to write that LCM is zero. We are going to write that LCM is not defined.
Not defined, yes.
Okay. Thank you, ma'am. We have learned new thing like from junior classes. Still, I was not knowing that much.
Okay.
For the
These
first
are
time,
some
I came to
trivial kind of
like
things actually, but
yeah.
still,
But
when
it's
we do
but
number theory.
yeah. Yeah. Ma'am, one more
And
thing.
yeah,
I'm very surprised here. Like this,
mhm.
I come to know that like this group theory totally was developed by Galva only, who was 14 years
Mm,
old. Or this I came to know that how come this 14 years child can has written this
we
all the
can't
things.
say he was a child.
Ma'am,
If like he can introduce this
I
thing, then he was not like for sure he was not a child.
just he was 14 years old and
Mhm.
I don't
And
know
still,
how he has gone through.
if you read the like autobiography or biography of that guy, uh, the situation, the circumstances were not even friendly for maths. There was a lot of struggles and something. But yeah, that's interesting. Hmm.
That's why, ma'am, I have the respect for this subject. Like, no, what is the insight for the
Hmm.
every person? Like, if we see, even a single contribution also, it means a lot, and that's why we enjoy
Yes.
like this thing because we so means sometimes when someone shows the path, so it seems to be easy, and we take it
Hmm.
okay, it's simple, but when we look into depth, no, then we realize ki what was the insight of that particular person, and then really we have the respect for them, and we have the
Yes.
respect for the teachers also, like you, everyone, like actually they make us understand that how to see the things, because without
Hmm.
I think guidance, we no one can understand these things. Thank you, thank you.
Exactly. Okay. So I think we should stop now. Any doubt for this session? Mm, yeah, I promise. Like I will make some separate videos for some special kind of groups. But for now, yeah, Vaibhav,
yes, ma'am.
you're saying something?
No, ma'am. I was just listening to, and I was very amazed to
Okay.
listen to all the conversations
Yeah, but
about.
I recommend like you must read the history, like what is the history of Gilva, what he do and how and like under which circumstances you will be amazed.
Yes, but what he said, Satinder, I mean, he said about the 14-year-old guy. I
Yes.
thought that he was some kind of reincarnation of any mathematician. Maybe
Mm, it may be.
maybe he just came to complete his work.
Yes, because this group theory, we study this in at least in our bachelor's first semester. So, like at least at an age of
Ma'am,
16, 17, I guess.
he died early
And
also. I
still
think
yeah, exactly.
Yes,
But
like
still at the age
what
of
the
16, 17,
he
and
died.
even sometimes now we find this theory, this subject, or some things difficult or challenging for us.
yes, like
So,
that is so amazing. Like,
yeah,
Like it's this application of group theory. Like if we are not going to understand this group theory, so we can't understand ring and field because totally it is based on
right.
that. And moreover, in the number theory field, a vast application of this is there. Then further, topology and further we go abroad, then again the same thing is
Yeah.
applied. So he opened the totally means this is the new concept of the things what due to that guy has happened. And not only him, each and every mathematician has a very great insight. Actually, ma'am, for us,
True.
like for me, it's like no, I didn't get the opportunity to study in the good universities because the a lot of competitive words are
I
there.
understand.
Although we are interested to study, but main thing is like if we are not getting going to get the good percentage marks, we are not going to get the admission because there are some guys who really understand the subjects and the seats are very limited. But this
Hmm.
online platform, we have got the opportunity to still learn because we are not interested in the marks or maybe something,
Right.
but to understand, to enjoy the
That's the
subjects.
beauty. We are
Yeah,
here just to learn something.
yeah, ma'am. And thank you, ma'am. Thank you a lot.
but
Okay, thank you.
ma'am,
Actually, this discussion was interesting for me also. Hmm. Thank you all. Yeah.
yeah,
Mm,
thanks for the session, ma'am.
okay, thank you. So, I'll stop the session here. I will upload some videos whenever I'll get some time. And yeah, that's all for today. Thank you.
Okay. Good night, ma'am.
Good night, ma'am.